Hi everybody, so this is Chris from Kane's Academy, and in the last lecture we talked about the simple linear regression and introduced some of the methods surrounding the simple linear regression. If you'd like to go back to that video at any point during this video, just click this top left arrow here and it will take you there. Likewise, if you'd like to skip to the next video at any point during this video, just click this bottom right arrow and it will take you directly to the next video. In this lecture, we're going to talk about OLS, or ordinary least squares method, as well as the goodness of fit measure r squared. So over here, I have a diagram that I've already drawn out, and we're just going to review some things to make them concrete. So x is our independent variable, y is our dependent variable, and what we're trying to do when we run a regression is measure how a change in x affects y. So what happens when we change x? What happens to y? And the way we do this is we have all of these observed data points. So these purple dots are all real life data. It's what we see in the real world. And then this green line here is our estimated regression, so our estimated relationship between x and y. And we can define this line as y hat, and y hat will be equal to some constant, or our intercept, beta naught hat, which is this distance here, plus our slope parameter, beta 1 hat, so the slope of this line, and then x. And so what we're going to start with is what is OLS? OLS is a method for estimating this this regression, the y hat regression, and it's essentially trying to put this line in the most appropriate way and defining it as our best guess for the relationship between x and y. And the way it does that is by minimizing the sum of squared residuals. So we talked about all of this in our last video, and I'll just quickly define the sum of squared residuals again as exactly what it sounds like. The sum of all of these residuals, so the distance, the vertical distance from this line to each point, squared. And now we should move ahead and talk about the properties of OLS. So we know that we're just trying to minimize our SSR, and that when doing that, we will basically find the most appropriate regression for our given data. And some essential properties we need to do this are as follows. So the sum of the residuals has to be equal to 0. So what does this mean? We've already defined that our residuals are equal to our true value for y minus our estimated value for y. And so that essentially means this value of y here for our this value of y here for our real point minus this value of y here for our estimated point at a given x. And so when we define it like this, if we can sort of interpret that if a point is below our estimated line, then our residual at that point will be negative. And if the point is above our estimated line, then that means that our residual at that given point will be positive. And so when we sum up all of these residuals, we want them to be equal to 0, because that will imply that the points are weighted equally, the true points are weighted equally above and below vertically on our line. Our second property that's very important for OLS is the sum of all the residuals multiplied by the x's will be equal to 0. Now, x is our independent variable, and essentially what property 2 is saying that the independent variable is not correlated with the residual. So this is very important because this property tells us, if it's true, it tells us that there's nothing in our residual that explains xi, because if we didn't have this property, then we wouldn't be able to properly use this regression as the relationship strictly between x and y. The third property is the mean of y, so y bar, is equal to beta 0 hat plus beta 1 hat times the mean of x. So this one might look a little bit more intimidating at first, but it's essentially very simple. What it means is that at some point on our estimated regression y hat, we have the value of the mean of the y values, as well as the mean of the x values. So on this line somewhere will be our y bar and our x bar. So when we minimize the sum of squared residuals, and we're using the OLS method or any other method, we will essentially want to know how well we have estimated the true model. And the way we do this is through goodness of fit measures. And there's one specifically we're going to talk about in this video, and it's called the R squared. And before we define it, we have to define some other measures of variation. So we already have the SSR, which is the deviation from the estimated line and squared. So essentially, if we have a low SSR, that will mean that the points are very tight to the line. They're all very close on this line. We have to define something similar called the SSE, which is the explained sum of squares. And this is defined as the sum of the estimated y's minus the mean and squared. So the SSE tells us what is explained by our model, how much is explained by our model in the y's. So how much of the variation in the y's is explained by our regression. We need to define one more before we can talk about the R squared, and it's called SST, or the total sum of squares. And the total sum of squares is defined as the sum of the true values of y minus the mean squared. So this, don't get these two confused. The estimated is our estimated parameter minus the mean, and this is the true value of y at that given x minus the mean. So this one tells us all of the variation in y, and this will tell us all of the estimated variation. So how much have we explained with our model, and this is how much is changing in the real world. So now that we have these three defined, we can define our R squared, our goodness of fit. How well does this estimated regression fit our true relationship between our independent variable x and our dependent variable y? And R squared is defined as SSE, so our explained sum of squares, divided by SST. And essentially this makes sense. We want to see how much of our model we have explained. So we have our explained sum of squares, which tells us how much of the variation in y we have explained using our model, divided by the total variation in y. And intuitively, we can derive this as also equal to the 1 minus the SSR divided by SST. So R squared will always be between 0 and 1, And so we take 1 and we minus what we haven't explained divided by the total variation. So both are equivalent, the SSE over SST and 1 minus SSR over SST. They are both equivalent measures. They're equal to the exact same thing. But we have to be very cautious because we've talked about causal relationships, and the R-squared does not tell us whether our regression is causal or not. It simply tells us how much we have explained using our regression. So be very careful. Do not confuse a high R-squared with a causal relationship. So the last thing we're going to talk about is how to interpret the R-squared. We're just going to quickly go over this. If R-squared is equal to 1, that means that every single point on in the real world lies exactly on our estimated regression. And if it's equal to 0, then that means that there's absolutely no correlation between our x and our y in our explained model. So the higher your R-squared, the better your goodness of fit, and the lower your R-squared, the poorer your goodness of fit. So that's all for our lecture today, and I encourage you to comment if you don't understand anything completely, or comment with feedback. We would love to hear your opinion. This is Chris, and we hope to see you soon.